Those of you that came to the dog talk this morning understand what dogs means. FHPS is I am a fellow of the Health Physics Society. That's an American society. I am a Canadian. I'm the only living Canadian that's been inducted into the fellowship of the Health Physics Society. So I'm very pleased about that. And the last bullet speaks for itself. I am a super geek, as evidenced by the pin that I'm wearing on my jacket. Some of you will recognize that. Some of you already know what it is because you can't stop asking questions, which is good. Questions are excellent. All right, quotes. First one from Benjamin Disraeli. There are three kinds of lies: lies, damned lies, and statistics. The second one from H.G. Wells. Statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And you know he's not wrong, to be able to understand how they're trying to lie to you. And the last one is from Samuel Johnson there. Round numbers are always false. You can do lots of things by rounding and making things seem better than they are. Now, language is an important device in trying to hide what's going on. As an example here, this was from an advertisement by a group of electrical companies, and we're going back in time in 1948, but nonetheless these tricks still apply. Today, electric power is available to more than 3/4 of US farms. So you get the idea that 3/4 of the US farms have electric power. Well, no, it's just available. They don't have it. But you're getting the wrong impression from the language. There's another one. I love this one. I've loved this one for years because it's very old. Nothing acts faster than Anodin. That's a headache medication. You may remember the name. All pain relievers actually act the same way, at the same speed. But the takeaway message from that first statement is nothing acts faster than Anodin, so take nothing, because it acts faster. They really shot themselves in the foot with that one, didn't they? We use models to make predictions, but if we put the wrong data in, we get crap coming out. So models can be very dangerous. Or, on the other hand, they can be very advantageous because you can put crap in, say you did a model, get crap out, and that crap could be useful in trying to support what you're saying. So you've got to be very careful when you're doing models. You've got to have a good model with good data to be able to get good results. And the only way to check it is, of course, to compare what comes out of a model and compare it to an observation, which we continually do. Now, the average is something that is really misused in many cases. When you think of the average, of course, you think that it's the most common. But what you probably don't know, there are 5 different averages. There's the mean, which is the arithmetic average. There is the median. There is the mode. They are related. Those 3 are related to each other, and if you have a perfectly normal distribution which follows a pattern, they are identical to each other. But when you don't, as data often isn't perfectly distributed, they differ from each other. Then we have the geometric and harmonic means, which you can use in certain circumstances. Most of the time, we're talking about the first one, the arithmetic mean. But sometimes that doesn't give you the result you want, so maybe you'll pick a different one. Let me give you an example using some synthetic data. The data that we're using is down here. It's just an arbitrary set of numbers I put together to show you how it comes out. And so the mean of that, the arithmetic mean of that series of numbers is 420. Well, maybe I don't like 420, maybe it's too high. So if I look at the median, which is the number that's in the middle of the ascending columns of numbers, then it's 10. And if I look at the mode, which is the most frequently occurring number in the series of numbers, then the answer's 5. And if I take the geometric mean, it's 14.2, and if I take the harmonic mean, it's 6.2. Now, depending on what I want to say with this series of numbers, I might pick one or another to try and prove my point. So when you see the average is such and such, you've got to know what that average is to be able to make a conclusion about the data that they're talking about. Here's an example. Corporation announces that its stock was held by just over 3,000 people, 3,003 people, and the average is 660 shares each. Well, that's true. But if you dig down into the data, it's also true that of the 2 million shares, 3 men had 1.5 million, and the remaining 500,000 was spread over the other 3,000 people. So they had an average of 166 shares per person. See how that data was manipulated? So just because you've got an average, it doesn't tell you the story. You've got to look at the distribution of the numbers. Here's another one. This is a good one. You see in a headline that says, users of snake oil get skin cancer half as much as those that don't, based on clinical trials. How often do we see based on clinical trials? There are 3 outcomes for users of snake oil. There's an increase in cancer rate. Not good. There's no change in the skin cancer rate because it's snake oil and it didn't do anything. And then there is actually a decrease in skin cancer rate, and that is the finding we want to be able to promote our product. How do we do this without lying completely? Because of course you can do that too. You can simply lie. Well, this is how you can do it. You can do it by taking small sample sizes. And I've used an example here of coin tosses shown in the table over on the right. The first column is result number 1, and you see the result of the coin tosses: heads, tails, 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 heads. 2 heads were in trial number 1. Trial number 2, it was heads, tails, tails. We had 2 heads again. But in trial number 3, no heads came up. And that's the result I want. So I take trial number 1 and trial number 2 and I throw them out the window. I use the results from trial number 3, which is valid, and say, there's my clinical trial, and here's my proof. Clever, right? They did a trial. They did lots of trials. They just didn't tell you about the ones that failed. But when you see things like this, you'll see that a test is accurate 19 times out of 20. That means 95% of the time the answer is going to be what you expect it to be. The corollary of this is 5% of the time the answer can be something else. And 5% isn't insignificant. Don't forget that 5% can occur. Yes, it's not great odds, but it can still be something else. Now, then there's other distributions. What's put up there on the screen applies to the distribution you see on the screen. That's called a normal distribution. It's like a bell curve, if you're familiar with the term bell curve. The data falls into that pattern. There are other distributions where it doesn't look as clean as that. Nonetheless, people apply these statistics to those distributions, which is completely wrong. You can't then make the conclusions. Here's a graph. Something's going up. Looks good. I'm trying to show that something's going up. Things are improving. Maybe it's the economy. Maybe it's the rise of employment rate. What is it? I have no idea. Why not? Because there's nothing on there. There's no y-axis. I don't know what the scale is. There's no title to this. I just see a rise. And there could be some arbitrary text around it. Another example. This is Planned Parenthood Federation of America. They are showing that abortions are up and that life-saving procedures are down. And as you can see from this diagram, from 2006 to 2013, we've got cancer screening and prevention services plummeting down, and over on the right we have abortions rising equally, it seems, from this diagram. What's hidden here? Well, there's no Y-scale. There are some numbers up there, but there's no Y-scale. You can't see anything beyond the arrows. Doesn't tell you anything. Let's replot that data now with a Y-scale. The abortion procedures now are the lower line. And remember the precipitous rise that we saw on the previous slide? It's not there. And similarly with cancer screening and prevention services plummeting down. Well, yes, they are decreasing, but that previous picture gave you completely the wrong idea of what was going on. Here's another example. Under President Obama, we have more students are earning their high school diplomas than ever before. We have years down the bottom, we have a pile of books, we have a percentage on top, and if we look from the left to the right, we see a small pile of books. Over on the right, we see a big pile of books. It looks like there's been a huge increase. Yes, the numbers are on top, but visually, we've got these big piles of books over on the right. Let's replot that information. We've got 5 books over on the left, 16 books over on the right. What does it mean? Nonsense. That's what it looks like if you plot properly. Not really a big change. Graphs are a great way to confuse you. So those are the rates, 75% over on the left, and over on the right, 82%. You should all move to Oklahoma, where our activity manager comes from, because the average temperature there is 60.2 degrees Fahrenheit. Isn't it just wonderful? No, you're shaking your head. Do you live in Oklahoma? No? Dallas? Well, that's different. What's this? What's hiding here? The range of temperatures is hiding here, because I've just given you an average. Now look at the ranges of the low and the high on the same graph. So yes, the average is 60.2, but you're going to go from minus 20 all the way up to about 110, depending on what day of the year. So I'm not necessarily sure that you should be moving to Oklahoma anytime soon. But the average there really hit things. Here's an example of no change from a set of data. You see this often now in climate change denial. You'll get a plot like this showing how the Earth's temperature has changed over the last few decades. It'll look like this. Well, let's say I actually want to show you that there's been a change, and I want to show you there's been a large change. I can replot this using a different y-axis. This is the same data, but now instead of going from 0 to 120, I'm going from 100 to 110. Now there's an enormous change. It's the same data. It's just the way it's being presented to you. You've got to look at the numbers to try and figure out what's going on. This is now a log graph. We're looking at the log of the mean horsepower of different engines. The first one is the hybrid. Next one is an SUV, then a sedan, a sport, a truck, and a wagon. The numbers are up on top of the actual horsepower. Now, a log plot is familiar to those who work in science. It allows us to put several ranges of numbers on the same graph. Otherwise, they get lost as we increase the decades. Notice on the left, the y-axis starts at 1. The next interval is 10, then the next interval is 100, and then the next interval will be 1000. So we're going up by powers of 10 on the y-axis. That's a log graph. If I now replot this in a linear form, which is what most of us are familiar with, we now see that the hybrid doesn't look so good anymore as it did in the previous slide. Previous slide, hybrid looks great compared to the others. Replot the data, hybrid is definitely underpowered compared to all the other vehicles. Let's say that company A produces more than company B. Let's say it's twice as much as shown in this bar graph. Company A is the blue column, and company B is the orange column. Maybe I want to exaggerate what company A is doing. I can replot this in a different format. I can do it in the form of a circle. The radius of circle A is twice the radius of circle B. That's where the factor of 2 is in there. Yet company A now looks much more productive than company B. The double y-axis. If you ever get a double y-axis, then look for how they're trying to delude you. We've got an axis on the left side, which is uninsured Americans. We've got an axis on the right side, which is unemployment rate. The blue line at top is the uninsured Americans, and the sort of olive line underneath is the unemployment rate. And they look like they're going up about the same. If you actually look at the data, you see that the uninsured Americans are going from 46 million to 49 million. That's a factor of 1.06, close to 1. Whereas the unemployment rate has risen from 4.5% to 7.5%. That's a factor of 1.6. So we've buried the difference between those two lines by choosing two y-axes. Always watch out for two y-axes. Now we get some really silly stuff. My favorite part of this talk is the silly stuff. We got a really weird time scale on this plot. The first part is last year, the middle is last week, and then on the far side we've got current. So that's a bit odd, nothing linear there. This is the cost of gasoline at a time. Last year it was $3.17. Last week it was $3.51, and current is $3.57. It's not current now. This is when that plot was done. Very strange, but you get the idea from this plot that gas prices are continuing to rise. Well, let's replot that now with a proper time scale. So that's what it looks like now. And as you can see, there is a rise indeed. It hasn't risen a great deal across from the year, and a little tick up at the end. Now let's go into the actual data that they didn't plot, which is part of this. So now here's the whole thing. So here's all the data for that time period from the government, from the US Energy Information. And we start at 3, which is the circle, and we end up at those last two also in the red circle. But what happened in between? Well, the cost actually went up, and then it went down again. So the original implication that the cost of gasoline has continued to rise over the last year is in fact a total fabrication, and is a lie. They are lying with statistics. We'll see more. This is the Bradford Liberal Democrats Facebook page at the time this was done, and it stated that the rate of mental illness was 1 in 4 per year. 1 in 4 per year. Adults were suffering from mental illness. The World Health Organization also agreed with 1 in 4, but it was over their lifetime. So we went from lifetime to per year. I don't know whether that was a typo or not, or an intentional thing. And the children's experience also was 10 to 20% in their lifetime too. Here are hypothetical responses to a question. This is the percent answer for yes and no to this question. And it looks like there are more no's than yeses. But look carefully at the y-axis, and then replot the whole thing with going from 0 up to 100%, and it looks like this. So the yeses are the blue line, and the no is that little thin line at the top. But by neglecting some of the data, I have deluded you into thinking the no's were the more prominent answer. Let's take an example of a hypothetical IQ test. We have two people, John and Linda, we would say, and their IQs are 98 and 101 respectively. Now the average IQ is 100, so we would say that perhaps John is not quite as smart as Linda, who is just over 100, and John is just under 100. Well, now let's go look at the test in more detail. All tests like this have an uncertainty associated with them, which sometimes gets lost when they publish numbers. So the test is only good to 3%. So now let's look at the data again. So John's data is 98 plus or minus 3%, and Linda's answer is 101 plus or minus 3%. There's an even chance that John's result is anywhere from 95 to 101, and Linda's result is anywhere from 98 to 104. There is no difference between these answers. They are statistically indistinguishable, and to claim otherwise is incorrect. Showing you here is a plot. These are bar graphs that show you the two IQ scores. I'll put on top the 99% confidence limit. You see how they overlap. If you ever get numbers like this where they overlap, you can't say there's anything different between the two numbers. This is range. And you'll see how the mean is moving up. And so we will have more occurrences in the extremely hot area as the mean moves up. We will have less occurrences in the extremely cold as the mean moves up. But we still have extremes in both ends. So where that mean is affects what happens to the extremes. Polling. Very important, trying to figure out what's going on with polling. If there's a prejudice already existing in the population when you're asking your question, you can either be misled into getting an answer that is wrong because you didn't understand what the question was that you were asking these people with a prejudice, or cunningly, you can use that prejudice to get the answer you want with that population. Give you an example. Maryland. Fewer than 2% reported getting less than 2.5 on their grade point average. But when you go back to the university data, in fact, 11% did. How come this poll is wrong? People lie. You'll see more evidence of that as I go ahead. In Maryland, again, 44% they donated to the university's alumni. When you look at who actually donated to the university, we find only 28% actually did. Again, they lied. So polling isn't necessarily the most reliable way of getting information. It would be perfect if we were all honest, but unfortunately we're not. We're going back to the Trump-Clinton election, and from the LA Times there's a quote there that Trump voters were noticeably less comfortable in telling a telephone pollster about their actual vote. And when you look at the popularity there, the blue line Clinton, a red line Trump, the prediction was that he was going to lose. But in fact, of course, he won, as you know. That poll was incorrect because they weren't getting the right information. November 2000. Some of you will remember when Ralph Nader was running for president. And what happened there was 9% said he was the only candidate worth voting for. That sounded really good. But in fact, he only got about 3% of the vote. What happened here? When they did the polling, they didn't pick a completely random sample of people to ask the questions. They ended up speaking to more people that supported Nader than supported either Bush, Gore, or Buchanan, as shown in the distribution there on the bar graph. So there was a disproportionate number of people that supported Nader during that poll, so they got the wrong answer. I call this the semi-attached. You get the idea that something is associated with something else because of the way it's worded. 27% of a large sample of eminent physicians use Duster more than any other brand. Doesn't matter what Duster is. Who says eminent physicians know anything about Duster? But you get the idea that because they know that Duster's great, then you should too, right? Acme's juicer extracts 26% more juice. Well, more than what? Hand-squeezed oranges in this particular case. And then more people were killed by aeroplanes last year than in 1910. Have you figured out the problem there? More people are flying now, so there's more deaths. This is one that we found when we were traveling. This is another example of the semi-attached. Doctor's Choice Pharmacy. Oh, well, doctors use this. I better go buy my stuff there. Karl Marx. Have we all heard of Karl Marx? Yes? Sorry? Very good. You know the book. This is a calculation of rate of surplus value of a mill. We assume the waste to be 6%. The raw material costs in round numbers £342. The 10,000 spindles cost we assume at £1 per spindle. The wear and tear we put at 10%. The rent of the building we suppose to be £300. There's a lot of weasel words in there. Let's carry on. The above data, which may be relied upon, were given to me by a Manchester spinner. Well, who says he knows anything about the operation of the business anyway? Anyway, we go on and we conclude from this. From those approximations, we get the rate of surplus value is therefore 80 over 52, which is 153 and 11/13%. For a 10-hour day, this gives him necessary labour for 3 and 31/33 hours and a surplus labour of 6 and 2/33. The accuracy of this implies knowledge that 6 and 2/33 is an accurate number. It's bullshit. It's meaningless. There's so many approximations and rubbish in this calculation that this is an example of garbage into the model and giving you garbage out. All a bluff. This was published in the Canadian Press in the Star, not exactly the best newspaper in Canada, but nonetheless. Statistics Canada reported the labour force had expanded by 22,000 jobs last month. This was in August of 2017. Unemployment had reached a record low of 6.2% at that point. Well, what do these numbers actually mean? What they hid in here was quite cunning, because what actually happened was there were 110,000 part jobs being created, but 88,000 full-time jobs had been eliminated, which was hidden under that statistic. Percentages. Oh, we can have fun with percentages. The men were given a 5% increase in wages that gave back to the men 1/4 of the 20% cut that they took last winter. 5 times 4 is 20, right? That's where we'll get that calculation from. Well, we've changed bases here. Let's use a dollar as an example for that. We cut 20 cents, and that's down by 20%. So we got the 20% cut. A 5% increase then on 80 cents is 4 cents, which is not 1/4, it's 1/5. See how the base changed there? Last month, I bought a pair of socks for $5. Last week, the store dropped the price of the socks by 25%. This week, they raised the price by 25%. So now the same socks I bought last month are selling for the same price, because 25% down, 25% up. Cancels out, right? No, doesn't. It actually would be $4.69. Here's another example. In 1970, 12.5 million children lived at home, or young people lived at home. The population of the country at that point was 234 million. The percentage living at home was 5.3%. In 2015, it was 18.6 million living at home. The population of the country had risen to just under 310 million. 6% were living at home. The difference between the people living at home between 1970 and 2015 was 48%. However, if you actually look at the percentages on the far right, it's not 48%. It's barely gone up by 1%. Again, percentages deluding you into something else. School grades. I won't go through these numbers in detail, but the amount increase of the 3 schools here is the same. It's 5. Yet when you compare it to the base numbers, the percent increase has gone from 25% to 10% to 5%. Because of the starting point we took our percentage. So you need to know that too to be able to evaluate percentages. A survey says that 169 corporations that replied to a poll said blah, 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 blah. Doesn't matter what they said. What you need to know is how many companies were actually polled. And in this particular case, it's 1,200, and only 169 replied. So what does that mean? Doesn't mean anything, really. Small numbers can give you a wrong conclusion. This is a biased sample. Actually, the FDA issued a warning letter to this company, which is quite a serious thing in the United States. The company claimed that 38% of people using this achieved a cytogenic response. That clinical trial used 26 patients, but in fact, the number of patients in the real trial was 48. They threw out all the results they didn't want to be able to get the answer they want. The true percentage was actually 14% when you looked at the study as a whole. That's why the warning letter was issued. Normalization is something that can give you a true answer when you get misled. So this statistic suggests that 16-year-olds are safer drivers than people in their 20s, and the octogenarians are very safe. The graph over on the right shows you the number of drivers in fatal crashes in 1988. So there's more drivers in the age group of 20 to 24 having fatal crashes than those of the age greater than 79. Let's go and look at this as a fact. We have to express this as a risk per miles driven, not just driving. So now we're looking at the fatal crashes per 100 million miles driven in 1988. And you see the picture's completely reversed. In fact, the riskiest drivers are the older drivers, not the youngest ones. So depending how you present that information, we can get two different answers. That's the right one, though. Consider these complaints about airlines. American Airlines had 253 complaints in the year 2016, United 156, all the way down to ExpressJet that only have 7. So we conclude from this data that who's the best airline to fly with? It's probably ExpressJet with the least number of complaints. SkyWest, Virgin, and ExpressJet had the least number of complaints. Let's look at it as complaints per passenger, as opposed to just the number of complaints. So this is now the number of passengers that they were carrying, and we see this picture has changed a lot. Spirit now has the most number of complaints per passenger. The best public schools, listen carefully to the words, the best public schools offer a more challenging curriculum than most private schools. Are public schools therefore better than private schools? You're comparing apples and oranges here, something that's common when people are trying to mislead you with statistics. You're being asked to compare the best public schools with most private schools. So we don't have the same samples. You can't say anything about this. This is another example. I'm not going to read this one out, but again, we're comparing two different programs here to try and give you a distorted picture of what's going on. And the key is these words: a well-run curbside program with a typical trash collection program. So again, you're comparing apples and oranges and you're not getting the real picture. Here's a great one. This is comparing welfare versus full-time jobs. 108 million people on welfare, only 101 million people fully employed. What's going on here? How come there are more people on welfare? Well, the way this data was collected is very cunning. If one person in the household, on a household of 10, is collecting benefits, then all 10 people in the household are lumped into that number. So that number can be out by a factor of 10. Workers can get benefits as well. They're still working, so they're double counted. So again, meaningless. This is data dredging. Japanese passenger cars sold in the US versus suicides by crashing of motor vehicles. It looks like there's good correlation here, that if you buy a Japanese car, then there's going to be more fatal crashes. This is absolute rubbish. Here's another one. This is the US spending on science, space and technology versus suicides by hanging, strangulation and suffocation. You want to increase the suicide rate, then spend more money on science, is what that graph tells you, which is also nonsense. This is data dredging. Normalization. People injured in New York State following a car crash. Drivers under the influence of alcohol is the blue wedge. Drivers not under the influence is the orange circle. So the majority of people not under the influence were involved in a car crash. So this kind of implies that if you drink, you're okay. Well, that's not true because, of course, they've added some other factors in there. This is the real data. The blue now is the drivers under the influence, and the orange is those that were not drinking. But it's even more complicated than that because we've left out a whole host of reasons, as shown on this pie chart, that shows you all the different reasons people got into problems. And the brown wedge is those that are alcohol related. So by ignoring stuff, you can get whatever result you like. In court, Juanita Brooks had her purse snatched. She said the snatcher was a blonde woman with a ponytail, and there was a bearded African American who had a moustache accompanying her. They escaped in a yellow car. The police arrested a couple matching that description. This was Janet and Mark Collins. They had a yellow car. They fit the description. They were taken to trial. Unfortunately, the prosecution had difficulties. First of all, Juanita couldn't identify either the defendant, despite the fact that she had described a blonde woman and a black man and a yellow car. And the witness also at the trial couldn't identify either of the defendants. Nonetheless, there was an expert witness brought in who proved that the Collinses were guilty of this crime. Now, how did he do that? He constructed a probability table, as shown here. What's the probability, for example, of owning a yellow car? That was 10%, and I won't go through all of those. And concluded from this, the likelihood of such a couple existing was 1 in 12 million. This is 1 in 12 million that matches that description. How did he get these numbers? Now, the math expert, by the way, was an associate professor at a local university. He went round secretaries in the motor vehicle pool and asked for their opinions on these probabilities. These probabilities are not independent. You can't add these and multiply them together in a normal way to end up 1 in 12 million. Nonetheless, the Collinses were convicted. Fortunately, when it went to the Supreme Court, they saw better, and the case was thrown out as being rubbish. Who remembers this? Joe McCarthy, 1950. I have a list in my hand of 205 members of the Communist Party. What was on that piece of paper that had 205 names of the Communist Party? Nothing. It's a lie. It's the biggest, most successful lie in political history to this day, I think. Although we've had some good ones. Here's a great one. This is the number. Research shows that lipozene, people taking lipozene lost 4 times more weight. Clinical trial. No link to that study was provided with this advertisement. And it also said that 78% of each pound lost was fat. There was no evidence ever found for this. I did track down the clinical trial. This is the clinical trial, despite the fact that they didn't tell me where it was. 20 obese female patients were in this trial. They weren't healthy to start with. 10 in a control group, 10 in the actual group taking the drug. The weight range I've shown up there, they were large people. This is not a random selection. The active group lost 5.5 plus or minus 1.5 pounds, and the control group put on 1.5 pounds plus or minus 1.5 pounds. Digging into the study, this uncertainty is a standard deviation of the mean, which is a reduced number. What we want is a standard deviation of the measurement, and when we reconvert that back to the standard deviation of the measurement, it goes up to 4.8. I think you're getting the idea now when you're looking at these numbers. I then recreated the data. They didn't provide the data, but I was able to recreate the data to get those averages, and that's what the data looks like. So we've got the initial weight of the people on the left in blue, we've got the final weight of the people in orange on the right, and basically when you look at this, it's a load of rubbish. Lipozene is snake oil. Extrapolation. If we have a set of data, we can maybe put a straight line through it and then make a prediction on that straight line. However, we have to, when we make a prediction, make sure that prediction lies within the group of data that we took to establish what the prediction was. Here is the data we studied. We've got a fairly good straight line there. Once we get out of that, we don't know what this function did. So if we make a prediction up here and we have no observable data, it could be rubbish. You've got to have observable data where you make predictions. Otherwise, you can't really conclude anything. Fox News 2012, this is a pie chart. This is the number of people, the percentage people that were backing various candidates. 70% for Palin, 60% for Romney, 63% for Huckabee. Little did Fox know that in a pie chart, the numbers have to add up to 100%. Not 193%. How concerned are you about the Zika virus? And from this graph, this is on NBC, you see that the big line is not at all, it's 13%. But look at the numbers. Ignore the bars. And this is just so misleading. Here's another one. This is the warmest year on record. It's out of date now, but nonetheless, we get the idea that 2012 was really warm compared to the other years. Why? Because it's red, and they've expanded the scale. We've exceeded that now. Another example, same thing. 1934 is often used by climate deniers because in this region of the world it was warm. Right there, you see where the orange and red is? Yes, it was warm. But in the rest of the world, it wasn't. If you look at the same graph in 2016, you see how 2016 was very much warmer than 1934. And last year, in fact, was even warmer than 2016. Survey, cold call interviews. Pollsters asked dentists to recommend multiple brands. So while 80% of the people polled mentioned Colgate, we've got no information about the other brands whatsoever. The advertisements were taken down. This is another one that's wrong. This is Tamiflu. Clinical trials. There were 11 clinical trials. Only 3 of them were used to make a conclusion. The side effects of this drug were ignored. So if 1 million people took it in a pandemic, you'd expect 45,000 to have vomiting, 31,000 to have headaches, and 11,000 to have psychiatric side effects. And when you go into the data, the actual improvement was only a 20-hour reduction in symptoms. All the other things they claimed were incorrect. This is what you have to ask when you're evaluating scientific and statistical data. Where's the source coming from? Who's telling you this? Where's the data? Does the subject change in the paragraph or paragraphs describing what they're trying to sell you? Does it make sense? Use some common sense, you can spot it there. Do you have incomplete or historical data that is cherry-picked? And are they using extrapolations to try and predict something they shouldn't be? A COVID example. Couldn't not have this one. Over on the left, we have how well Argentina did in COVID tests compared to other countries. So Argentina's the blue line. Then we have the United States, Italy, Germany, and Norway. We replot that properly, and that's shown over on the right. And you can see how well Argentina did. Not very well at all. They were trying to convince people they were doing better than they were. And that brings me to the end of how you should spot the lies in statistics. At 10:15 tonight, weather permitting, up on the top deck, we're going to do some stargazing. Look for details in your program.